last lesson in this unit, and it's going to be on Hooke's law. In the last video, we learned about potential energy, and it represents stored energy, which is available for use if and when required. So far, we've only looked at gravitational potential energy. The other type of potential energy is stored in a spring. Hooke's law states that the amount of deformation in a spring is proportional to the force applied to deform it and can be expressed as force is equal to kx, where x is the distance of the stretched or compressed string and k is the spring constant. That spring constant can vary. It really depends on how flexible that spring is, and you played around with springs before, so if you compare the different ones, you can have really stiff springs or really loose springs, and this would depend on the spring constant. So the work being done on a spring is expressed as W is equal to a half kx squared. Again, where k is your spring constant and x is the distance of the stretched or compressed spring. When you stretch a spring, the work done goes into stretching the spring and is stored in the spring as potential energy. So your potential energy is that work, which is a half kx squared. We are going to use this result and the force one from above. So let's go ahead and do an example of this. Find the spring constant for an ideal spring that requires 12 newtons to stretch 1.2 meters. So force is k times x. We are looking for k in this case, so I'm going to divide both sides by x. Force is 12 newtons, x is 1.2 meters, 12 divided by 1.2 is 10, and our units are in newtons per meter. How much energy is stored in the above spring if it is stretched 2 meters? So we're looking for the potential energy being stored in that spring. It's calculated as a half k x squared. We just found k, and that's 10. And we are stretching the spring by 2 meters. So a half times 10 times 2 squared is 20. 20 joules. If the compressed spring is set between a 4 kilogram mass and a wall, then released, how fast will the mass move once the spring is decompressed? So our potential energy is going to become kinetic energy, and it will be conserved. So then potential energy is going to equal kinetic energy. Our potential energy, we just found that over here, which is 12 joules. Kinetic energy is calculated as a half mv squared. And again, this is from our last video and our last lesson. Our mass is 4 kilograms, and we're looking for V. 4 divided by 2 is 2. Then I'm going to divide 2 on both sides, so V squared is 10. Lastly, I'll square root both sides in order to get V by itself, so this will be 3.2 meters per second as our final answer. Moving on to the next example, you probably don't have this typed out in your notes, so go ahead and write this down, and then when you're ready, press play, and we're going to go through this solution. So in example 2, we have a 10 kilogram cannonball. It sits on a spring. The spring constant is 50,000 newtons per meter, and it's compressed by 95 centimeters. How high does the spring shoot the cannon? And we want to know the speed as it leaves the spring. So we have two parts of this question. The first thing I'm going to do is find our height. The height of the cannonball. So for our x, we know the cannonball is going to sit on the spring and compress that spring by 95 centimeters. We need to change this into meters, so I'm going to divide this by 1,000, which is 0.95 meters. Sorry, I'm going to divide by 100, not 1,000, to get 0.95 meters. Now, thinking about our equation we're going to use, potential energy plus kinetic energy will be our total energy. And I'm going to consider the total energy while it is on the spring. Our energy is going to be conserved, so it's going to equal to the potential energy and the kinetic energy when our cannonball's in the air at its peak. If we think about this scenario, when it's on the spring, our cannonball is not moving at all. So it has no kinetic energy. And even when it's at its peak, there's no kinetic energy there either. If you think about this picture, let's just say our cannonball is moving up, and we're looking at the very specific point over here before it comes back down. Just like your free fall questions, our ball isn't going to move, or our cannonball is not going to move at that peak time. So all it has is potential energy stored for it to come back down, but there's no kinetic energy there. So that means that we are left with potential energy when it's on the spring and potential energy when the cannonball is in the peak in the air. Our potential energy on the spring is calculated as a half kx squared. Our potential energy when it's in the air is mgh. Now I'm going to fill in the information we know. So k is 50,000. Our x is 0.95. The mass of our cannon is 10. Acceleration due to gravity is 9.81. We're looking for the height of the cannon. So I'm going to rearrange and solve for h. So just simplifying our left-hand side, we are going to get 22,562.5 and 98.1 on our right-hand side. Then I'm going to divide both sides by 98.1. So our height of this cannon is going to be 230 meters. That's one solution. So again, the first thing I did is change our distance to meters. Then I had to figure out our equation we're going to use by comparing the total energy and the two different scenarios, and that energy is conserved. Then I changed it, your potential energy, to the specific formula depending on which scenario we're looking at. So our potential energy on the spring and our potential energy when the cannonball is in the air. Then I plugged the information in and solved for our height. So now the second part of our question is asking about at the speed that our cannonball is leaving the spring. So for our speed, our potential energy while it's on the spring is going to convert into kinetic energy, and this energy is conserved. Our potential energy we found before. It was actually over here. So we found it PE, which is this, and we found it, which is this. So I'm just going to put that down here as our potential energy. just so I have to recalculate everything again. And kinetic energy is calculated as a half mv squared. So I'm just going to replace m because we know what that is. It's 10. And then I'll rearrange and solve for v. So v squared then is 22,562.5 divided by 5, and then we're going to square root both sides. So v is 67.2 meters per second as our final answer. Moving on to our last example, a 2 kilogram ball is thrown downward with an initial velocity of 10 meters per second from a 110 meter building. The ball lands on a spring. The constant is 10,000. How much does the ball compress the spring? And we also want to know how high does the spring then launch this ball? All right, again, there's two parts to this question. So I'm first going to look at how much does the ball compress the spring, and that's x, so that's what I'm looking for. I'm going to compare the two scenarios. The total energy when the ball is about to be thrown our energy is going to be conserved. And this scenario is when the ball has finished dropping and compressing the spring. So when the ball's about to be thrown, it's going to be in the air. So here's our ball. It has a potential energy without you even throwing it. It wants to fall to the center of the earth. So that means we do have potential energy there. We also have kinetic energy because it's going to be thrown. It's not going to be dropped, but thrown with initial velocity. So we also have kinetic energy as well. If we're just simply dropping the ball, then we won't have any kinetic energy, but because we're throwing it, we will have kinetic energy. On the other side, if we're thinking about the ball finish compressing that spring, we're not going to have kinetic energy anymore. We just have potential energy that's being stored in that spring. So the ball is no longer moving in this scenario. So we have PE plus KE is equal to PE2. I'm going to replace our potential and kinetic energy with the actual formulas. So our potential energy when the ball is just hanging in the air is calculated as mgh. Our kinetic energy is a half mv squared. The potential energy of the ball as it's being held in the spring is a half k x squared. So now I'm going to go ahead and plug in all the information we know. So the mass is 2, acceleration due to gravity is 9.81. Our height is the height of the building, which is being thrown down at, which is 110 meters. Again, our mass is 2. The velocity that's going to be thrown down at is 10 meters per second. The constant of the spring is 10,000. We are looking for x. So just as a recap, this part here is the energy of the ball in relation to the earth as it wanting to fall down because of gravity. This is energy of the ball as it's being thrown. And here is the energy of the ball as it's being held in a spring. Notice that when I write energy, I put NRG. It's just a short form, and an easier way just to write energy when I had to write it down so many times. Okay, so I'm gonna go ahead now and simplify this. So we need to rearrange and solve for x. 2 times 9.81 times 110 is going to give us then I'm going to divide both sides by 5,000. And then square root both sides. So x is 0.6717 meters. Now we're going to look for the height of our ball. So we have the potential energy coming from the spring, which is equal to the potential energy when our ball is in the air at the peak. So our temperature diagram, if you want to have that, this is the potential energy as the ball is being held in the spring, and it's going to go up. We're looking at the potential energy when the ball's in the air at the very peak. So when it's in the spring, it's going to be a half kx squared. When it's in the air, it's mgh. So I'm looking for h because we're looking for the height of this ball. I'm going to fill in the information we know. K is 10,000. X we just found is 0.6717. The mass of the ball is 2. Gravity is 9.81. And we're looking for h. So once you rearrange and solve, you should get 115.1 meters as your final answer.